Let's look now at some definite integrals. Now these look like integrals, but they just have additional numbers on our integration sign. And that's because I want to integrate between the limits of 1 and 4. So how do we deal with this? Well, to start with, we do exactly what we know how to do with integration. We increase the power by 1, divide by the new power. We increase the power by 1 and divide by the new power. Not forgetting my constant of integration. Now I'm going to use a set of square brackets to indicate that I still haven't used these values. Let's just tidy this up quickly first. So that's going to become x cubed minus a half of x squared plus c, evaluated between 4 and 1. And there's the cat out of the bag. What we do with this definite integral is we evaluate it first at 4, the higher value, and then we evaluate it at 1, the lower value. And we subtract one from the other. So I'm now going to move to the next line and write down 4 cubed minus a half of 4 squared plus this constant minus 1 cubed minus a half of 1 squared plus this constant. This gives me 64 minus 8 plus the constant minus 1 minus a half plus the constant, which is going to be 56 plus the constant minus a half plus the constant, which hopefully we should notice by this point that the constant is going to cancel out, and I'm going to get left with 55 and a half, or to write that in a different way, 111 over 2. Now this constant will always cancel itself out, and you can sort of take a moment to realise why that's going to be. We put the constant of integration in. When we substitute the values in, it doesn't actually change the value of the constant, and we're always going to end up wiping the constant out. So typically what is done is we ignore the constant completely. We don't even write it down in any of our workings. Now, I think there's a slight danger in that, in the fact that if we're doing an indefinite integral, then we do need to remember to put this c in, and I think that causes some confusion. So sometimes maybe it's best to leave it in and just realise that it cancels out. Why do we do this? Why do we use definite integrals? Well, definite integrals are very useful when we want to find the area bound by a region on a graph. So here, the region bound by the function f of x and the x-axis will be given by integration. So if I wanted to find the area of this region here, the area of A is going to be the integral from A to C of the function f of x with respect to x. I always take my lower x value first and my higher x value after. So if I wanted to find the area in here, which we shall refer to as B, I would be integrating between C and B the function f of x with respect to x. So integration primarily used, certainly for A-level maths purposes, in finding areas bound by curves and the x-axis. So obviously the next question is about an area which is bound by a curve and the x-axis. The first thing I'm going to do with this is to sketch it, just so that we know what we're dealing with. I know that's going to be a negative quadratic. I know it's got roots at -2 and 1, so it's going to look something like this. And I'm interested in the region bound by the function and the x-axis. So the only area that's bound, the only area that's enclosed, is going to be this area in here. So what am I looking to do then? Well, we know that we want to integrate between -2 and 1 the function, which is 1 minus x plus 2 with respect to x. And we work this through carefully to say that we're going to have the integral between -2 and 1. First of all, I'm going to expand the bracket, and if I do that, I end up with 2 minus x squared, which I want to integrate with respect to x. Now, integrating that, I've got 2x, I've got x squared, and then I need to divide by 2, so that's going to give me this, and then this will become x cubed, divide by 3, stick on the coefficient. Messy, messy handwriting. I need to put on my bounds, 1 and -2. Let's tidy things up in here so that we can see clearly what we're trying to do. We've got 2x minus a half of x squared minus a third of x cubed between 1 and minus 2. So we start by substituting in the higher value, the value at the top here, which is going to be 2 lots of 1 minus a half of 1 squared minus a third of 1 cubed. And from that I want to subtract 2 lots of minus 2 minus a half of minus 2 squared minus a third of minus 2 cubed. Negatives are not your friend here. Often mistakes come in. So this is going to give me 2 minus a half minus a third. And in the second bracket, being very careful with the negatives, 2 lots of minus 2, that's minus 4. Minus a half, lots of negative 2 squared. Negative 2 squared is 4 positive, times by the negative half is going to give me negative 2. And then finally I've got negative a third, lots of negative 2 cubed. Negative 2 cubed is negative 8, times by the negative third gives me plus 8 over 3. And at this point I resort to my calculator to find out that that's going to be 7/6 minus, and this works out to be minus 10/3. Minus minus gives me a plus, so adding those two values together gives me 9/2 as my answer. Now here we're finding an area, so I like to write this down as 9/2 units squared to indicate that it is an area that we found. And that's how we would find an area bound by a curve.